What's up, party people? First of all, good morning. It's bright and early in the morning, and if you're watching this live, you might be up watching math YouTube videos this early in the morning. But do me a good favor and like, share, and subscribe. If you're one of my students watching this, do me a good favor, like, share, and subscribe. I want to get this information out to kids all over the world, as well as parents. I'm not going to take too much time because we need to get right into the content. This is Unit 6, Lesson 16, and this is going to be helpful for you to complete your work on today. Also, I know we had to kind of go fast yesterday in the classroom. So let's get right into it. And we're going to see because, no, that's not it. Give me a second. Let me make sure I have the right. I want to make sure I got the right file. So let's do share. What am I sharing? Let's see. I don't want to share my desktop. Hold on. No, that's not what I want to share. Hold on, y'all. We want to share this. All right, so not okay. There we go. Here we go. Let's get it. Let's present this. And we're talking about reasoning about exponential graphs. All right. And so we're not going to go through every piece in this lesson, but we're going to go through most of it. So here it says, this is the warm up. Jada received a gift of $180 in the first week. She spent a third of the gift money. She continues spending a third of what is left each week thereafter. Which equation best represents the amount of money G in dollars she has after T weeks? Be prepared to explain your reasoning. Okay, so let's go through why each is not. Okay, so this can't be it because actually this right here is linear. Now, the subtraction piece does add up, but this is linear. Remember, this unit is about exponential. This one right here, B might be a choice, but here's the problem with B. She's spending that 1/3, and remember, the growth factor needs to be what's remaining after the 1/3. So B is not correct. C, the initial value is incorrect. This is basically showing that she starts with 1/3, and then it's multiplied. So that's not it. This D is correct because the initial value is 180. The growth factor is 2/3 because she's spending 1/3 of the money every week, and then 2/3 of it is left, and then we multiply that exponentially. All right. Let's go to the next one. Excuse me. So here we go. We have each of the following functions. F, G, H, and J represent the value of an investment in a different company in dollars as a function of time, X in years. They are each written in the form M of X equals A times B to the X power. Okay. So when we look at this one, we're going to graph this in Desmos, and then we're going to explain how changing B changes the graph. Okay. So I want to go ahead and get right to the meat and potatoes of this. Notice we have each function here. So the red function is 50 times 2 to the x. The blue function is 50 times 3 to the x. The green one is 50 times 3 halves to the x. And the purple one is 50 times 0.5 to the x power. So let's break down what we see in each of these graphs. Let's start with the purple one, right? So notice the purple graph, actually, we're just going to focus on from the initial value over to the right. If you notice, each of these have the same initial value. So they all start out with the 50. So that's why we're looking at this central point right here. But if we look at the purple one, notice when it goes from left to right, it goes down, okay? That is because this growth factor is between 0 and 1. And so what that's saying is it's taking half of that 50 and multiplying by half of it. So it starts with the 50, and then if you notice, it's 25 here, then half of that, which would be 12.5, which half of that, half of that. So that's why that growth factor for purple, because the growth factor is between 0 and 1, that graph is going down. Now, if we go to the next one, let's look at the growth factor of each of these. And the growth factor for, go back up to the red now. The growth factor here is 2, okay? So the growth factor here is 2. This growth factor, 3 over 2 is 1.5 or 1.5, and this one is 3. So let's start with the green because it has you have 1.5 growth factor, you have 2 growth factor, and you have a 3 growth factor. So let's go with the smallest one. Notice the green one, it stretches out the furthest here. And then the 2, the red, it stretches out a little bit less than the green one. And then the blue one, notice it stretches out the least, okay? So let's think about why that is. When we look at these different points, right, I'm going to basically say this. So I'm going to put a point right there. So all of these functions reach 400, right? So here's a y value of 400. But if you notice, it takes less time. It takes the least amount of time for the growth factor of 3 to reach 400. And then it takes a little more time for the growth factor of 2 to reach 400. And then it takes the most time for the growth factor of 1.5 to reach the 400. Okay. So we can basically say when we change B, the amount grows. It's going to change how fast the amount grows. So the lower B is, above 1, remember these are values greater than 1. So if B is greater than 1, the smaller it is, or the closer it is to 1, the longer it takes for that amount to grow, okay? Versus when we increase that, if we go from 1.5 to 2, that amount grows faster. So as you can see, it takes more and more time, or less time, the larger the growth factor is. So this is very, very important. So B determines how fast the initial value grows or decays, because we don't want to forget the one that is less than 0, okay? So that's that. Now let's look at another example, right? Here we have 3 more functions. And notice in this case, these functions, they are actually, they have different initial values. Okay, so we'll go straight to this slide. These ones have different initial values, right? 10 here, 40 here, and 100 there, but they also have the same growth factor. So A is different in this case, and B is the same. So when I look at this, I want to see the fact that here for, let's start with red because it has the least amount of initial value. So that's the lowest on the y-intercept. And then the 40 for the blue one, it's a little higher on the y-intercept. And then the green one has 100 for the initial value. So it's a little higher on the y-intercept. But if you notice this distance here, because they have the same growth factor, okay, these graphs will always stay the same distance apart as this graph increases. Okay, so as the x value increases horizontally, they will always stay the same distance apart. They just have a different beginning part because of the initial value. Okay, some people say steepness. That's one way to describe it, but notice they have a different initial value, but when they have the same growth factor, they will always stay the same distance apart on that graph, okay? So we can see that when we change A is going to change. So A changes the y-intercept of the graph, okay? So A changes the y-intercept of the graph. Very, very important information. It's going to make it go up or down on the y-axis, okay? Let's go on to the next one. Activity 2. So here we want to match each equation with a graph, right? So you have these four functions. M of x equals 200 times 1/4 to the x. So notice all of them have the same initial value of 200, but they all have different growth factors. Okay. Now notice all of these growth factors are fractions. So that's why all of these graphs go down as you go from left to right. So let's see which one goes where. Okay. Now, based upon what we learned in the previous example, we can actually say, okay, so which one has the largest fraction of a growth factor? That's going to be number 4. So that actually is going to decrease the least amount each time. So this is going to be graph A. All right. And then after 7/8, between 3/4 and 1/2 and 1/4, 3/4 is the next largest. So that's going to be graph B. And then 1/2 is going to be graph C. And 1/4 is going to be graph D. Okay. So notice the larger the fraction in the growth factor, remember, these are fractions that are less than 1. All right. So the larger that fraction, the less that graph is going to decrease over time. Okay. So that's that. Let's clear that out and go on to the next one because the next one's getting a little more tedious. All right, so here we go. It says which function is decaying more quickly? In this case, this one is decaying quicker because it has the smallest growth factor. So what this is saying, from this $1,000, 1/10 of it is left. All right, so which one is decaying more quickly? F of x is decaying more quickly. Okay. And you can actually see this on a graphing calculator. Or on Desmos. I don't want to do it right now. So 1/10 of 1,000 is $100 versus 9/10 of 1,000 is $900. So if I go from 1,000 to 100, clearly it's going to decay faster. Okay. Here we skip all the way over to activity 4. Activity 4 is very, very important, right? So it says, here's a graph representing an exponential function f. The function f gives the value of a computer in dollars as a function of time x, measured in years since the time of purchase. Based on the graph, what can you say about the following? The purchase price of the computer, that's going to be the y-intercept. So this is going to be $400. Okay. The value of f when x equals 1. Now, this is interesting because there's a pattern. You may not see it. Notice there's a x value of 1 that's missing and an x value of 3 that's missing. So this would be 1, this would be 3. Now, we could simply estimate and see right here that that's roughly $200, right? Based upon where they meet. So I'm going to say $200. But also, if we look at that, then that means this right here would be about, so this would be 1 and 200. And then this would be 3 and 50. Okay. So now notice, is there a pattern? 400, half of that is 200, half of that is 100, half of that is 50, half of that is 25. Okay. So that's one way we could do this. The meaning of f of 1 means the value of the F computer was $200 after 1 year. Okay, that's what that means. Now we're going to clear this out and we're going to answer some other questions because we need to know something else. So here we're going to have to come up with an equation for this. It says how the value of the computer is changing each year. So it is decreasing by 1/2. Now, right now we have not calculated that, but we will. Okay. So let's see. Here we go. An equation that defines f. F of x equals, it starts out with $400. That's the initial value. Okay. Times 1/2 to the x power, okay? And it says whether f will reach 0 after 10 years. So f of 10 equals 400 times 1/2 to the 10th power. So that's a 10. Okay, so when we do this, this is going to be f of 10 is roughly 0. Like 39 cents. It's a longer decimal. Okay, so will it be 0 after 10 years? No, it's actually just below. It's 39 cents after 10 years. Okay, and you can plug in these values. Like if I plug in 2 for x, then you will get 100. Okay. Next. Here, activity 4, this part. Now we've got to create. It says here are graphs of two exponential functions. For each graph, write an equation that defines the function and find the value of the function when x equals 5. So in order to find the value of the function, I say a times b to the x power. Okay. So in order to find a, my initial value, boom, that's 5. So a equals 5. Okay, now I've got to find B. So B, in order to find B, I've got to actually do the ratio of 15 over 5 because I'm taking this y value over this y value. And I could also do 45 over 15. So it's taking this y value over this y value. So 45 over 15 is 3. 15 over 5 is 3. So now, as we can see, the common factor B is going to be 3, okay? And if I do, looking at the initial value of y, 5 times 3 is 15. 15 times 3 is 45. So now I can say f of x is equal to 5 times 3 to the x power. So that would be that equation, okay? If we do the same thing here, notice this is decay. So because it's going down from left to right. So since it's decay, we know this B actually should be between 0 and 1. So A, my initial value is 20. And B is going to be, we can say B is going to be, let's say, we can go, we can do 20 over 40. We can do 5 over 20. I'm sorry, not 5 over 20. That's not correct. Because the reason why we can't do 5 over 20 is because we're missing the value when x equals 1. Okay, so this is -1 to 0. So I could do 20 over 40, and that's 1/2, right? We don't know what the y value is when x equals 1. Okay. Or we could also say, so if we want to go from 20 to 5, we can basically say that some number squared, so let's just say x squared equals 5 over 20, okay? And x in this case would represent the growth factor, right? So what this is saying is some number to the second power equals 5 over 20, okay? But we don't necessarily have to do that in this case because we already see that the growth factor is 1/2. If you notice, I go from 40 when x equals -1 to 20 when x equals 0. So that decreases by 1/2. All right, so B is equal to 1/2. So I can say f of x equals 20, that's my initial value, times 1/2 or 0.5 to the x power. And that gives me my function. Now, if I want to find out what f of 5 equals, 5 times 3 to the 5th power. And I don't have my handy dandy calculator. So let's see. I got to go back into my book. I didn't write this part down, I don't think. Actually it is 1,215. So 1,000 f of 5 equals 1,215. Here f of 5 equals 20. times 1/2 to the 5th power. And so f of 5 here equals 0.625. All right. Boom. Now, I'm going to go through this one really quickly because time. I don't want this video to be too long. It says here are graphs representing two functions and descriptions of two functions. Function f, the area of a wall that is covered by mode A in square inches. Doubling every month. That's important. Doubling every month. All right. Function G, the area of a wall that is covered by mode B in square inches, tripling every month. Okay. Which graph represents each function? Label the graphs accordingly. Okay. So the first one is doubling. That means it's multiplying by 2. Function G is tripling, so it's multiplying by 3. So the growth factor on function G is higher than the growth factor on function F, which means that would have to be, G would have to be here, okay? The solid line. And so then F would have to be here, the dash line, because it doesn't say, we don't know what their initial value is, but we do know as they grow, the one that triples is going to grow faster. So that means this solid line would be G of X and the dashed line would be F of X, okay? So that's that. Let's go to the next one. So we know the solid line is G, the broken line is F. And so then it says, when the mole was first spotted and measured, was there more of mode A or more of mode B? Now, do not let this confuse you because we have G and we have F, but G has mode B. F has mode A. So here, that tells us there was more of mode A. More of mode A. Please don't let that confuse you. You got to read this carefully. All right. And then let's go to the next one. What does the point PQ tell us about the situation? Notice PQ is where they cross, okay? So this point tells us the time in months, excuse me, when the amount of mode A and B was the same. Okay? It tells us when the mode was the same because they're intersecting. All right. So this just tells us at what point, how many months it took for the mode A and mode B to be the same amount. All right. Very, very important. Your cool down is based on this as well. So please use this video to help you with your cool down. I think that is it for this one. Stop. All right. So hopefully this was helpful. Do me a favor, like, share, subscribe. Stop it, rewind it. Things that you don't understand, go back, pause, and things like that. Remember, if you have a question, you can post it in the comments on this video. Perfectly fine with me. I do respond to all the comments. It's bright and early, 6:24 in the morning. Y'all go out and have a phenomenal day. And